Another day, another story. Quantum entanglement is a phenomenon in quantum physics where two or more particles become interconnected in such a way that the state of one particle instantly influences the state of another, regardless of the distance between them. This means that if you measure the state of one particle, you can instantly know the state of the entangled partner, even if they are light years apart. Key features of quantum entanglement. Welcome to Tabo Eminent Channel. Non-local correlation. Entangled particles exhibit correlations in their physical properties, such as spin, polarization, or momentum, that are stronger than what would be possible under classical physics. This correlation persists even when the particles are separated by large distances. Instantaneous connection. The change in the state of one particle seems to be instantaneously reflected in the state of its entangled partner, a phenomenon that Einstein famously referred to as spooky action at a distance. Superposition. Before measurement, entangled particles exist in a superposition of states, meaning they don't have definite states until one of the particles is measured. Upon measurement, the superposition collapses, and both particles assume definite, but correlated, states. Violation of local realism. Quantum entanglement challenges the classical notion of local realism, which states that objects have definite properties independent of measurement and that information cannot travel faster than the speed of light. Entanglement suggests that particles can be instantaneously connected across distances, a concept that doesn't fit within the framework of classical physics. Applications of quantum entanglement. Quantum computing. Entanglement is a fundamental resource for quantum computers, enabling them to perform certain calculations much faster than classical computers. Quantum cryptography. Entangled particles can be used to create highly secure communication systems, as any attempt to eavesdrop on the communication would disturb the entanglement, alerting the communicating parties. Quantum teleportation. This is a process by which the state of a quantum system can be transferred from one location to another, using entanglement as a resource. History and development. Quantum entanglement was first introduced by Albert Einstein, Boris Podolsky, and Nathan Rosen in 1935 in what is now known as the EPR paradox, named after the author's initials. They presented a thought experiment intended to demonstrate that quantum mechanics, as it was understood at the time, was incomplete. Einstein and his colleagues were uncomfortable with the idea of entanglement because it seemed to allow for faster-than-light communication, which would violate the theory of relativity. They called this spooky action at a distance and believed it highlighted the need for a more complete theory that would explain these correlations without violating classical ideas of locality, that objects are only directly influenced by their immediate surroundings. However, the concept of entanglement gained more ground with the work of physicist John Bell in the 1960s. Bell developed a theorem, now known as Bell's theorem, which provided a way to test whether the predictions of quantum mechanics, including entanglement, could be explained by any local hidden variable theory. Essentially, Bell's theorem showed that no local hidden variable theory could reproduce all the predictions of quantum mechanics. This set the stage for experimental tests of quantum entanglement. Key experiments in the 1970s and 1980s. A series of experiments by physicists like Alain Aspect and his team provided strong evidence in favor of quantum entanglement. These experiments showed that particles that were entangled exhibited correlations that could not be explained by any classical means, thus supporting the predictions of quantum mechanics and suggesting that entanglement was a real phenomenon, not just a theoretical construct. These experiments typically involved pairs of photons that were entangled in terms of their polarization states. When measurements were made on the polarization of these photons at distant locations, the results were found to be correlated in a way that defied classical explanation, supporting the idea that measurement of one photon instantaneously affected the state of the other, regardless of distance. Thought experiments and interpretations. Entanglement has also been at the heart of many thought experiments that have helped shape our understanding of quantum mechanics, Schrödinger's cat, Erwin Schrödinger, another pioneer of quantum mechanics, formulated a thought experiment involving a cat placed in a box with a radioactive atom, a Geiger counter, a vial of poison, and a hammer. According to quantum mechanics, until the box is opened and an observation is made, the atom is in a superposition of decayed and undecayed states, and the cat is simultaneously alive and dead. This paradox highlights the counterintuitive nature of quantum superpositions and entanglement, as the fate of the cat is entangled with the state of the atom. Quantum teleportation. This concept involves transmitting the quantum state of one particle to another distant particle without any physical transfer of the particle itself. In 1993, a team of scientists, including Charles Bennett, demonstrated theoretically that, using entanglement, it is possible to teleport quantum information. Experiments have since successfully demonstrated quantum teleportation with particles like photons and atoms, which has exciting implications for future communication technologies. Wheeler's delayed choice experiment, proposed by physicist John Archibald Wheeler, this experiment is a variation of the famous double-slit experiment. It explores how choices made in the present can seemingly affect the past behavior of particles. In some versions involving entanglement, decisions made about how to measure entangled particles can appear to retroactively determine the state of the particles at an earlier time, further challenging classical notions of causality. Implications and applications. Quantum entanglement has profound implications for our understanding of reality and has led to several groundbreaking technological advancements. Quantum cryptography. Quantum entanglement provides a foundation for quantum cryptography, which offers potentially unbreakable encryption. If two parties share entangled particles, any attempt by an eavesdropper to intercept the communication would disrupt the entanglement, making the intrusion detectable. Quantum computing. In quantum computing, entangled qubits, quantum bits, can perform computations that are not feasible for classical computers. Quantum entanglement allows quantum computers to process many possibilities simultaneously, greatly speeding up certain types of computations, such as factoring large numbers, which has significant implications for cryptography. Quantum networks and the quantum internet. Entanglement can be used to link quantum computers over long distances, creating a quantum internet. This could enable secure communication, distributed quantum computing, and new forms of quantum-enhanced sensing and metrology. Challenges and open questions. Despite its many experimental confirmations, quantum entanglement still raises several philosophical and practical questions. For instance, the nature of quantum measurement and the role of the observer in the quantum realm remain hotly debated topics. In conclusion, quantum entanglement is not just a quirky feature of quantum mechanics, it is a profound and essential aspect of our universe that continues to challenge our understanding of reality, providing both deep philosophical questions and practical technological opportunities. Thanks for watching. Request you to subscribe the channel.